I want to welcome everyone to the 7th Symposium of Rising Scholars. We have 4 wonderful speakers here who will be sharing more about the work they've done over the past few months. Please join me in welcoming them. And the first speaker will be Ram Sivaraman, and he will start sharing his screen. And Ram, please introduce yourself.
Hello, my name is Ram Sivaraman, and I'm from Austin, Texas. So my project was about generalized and robust quantum generative adversarial network model, and I was mentored by Yash Chandan. So over the course of this presentation, I would like to cover a few main topics. We'll first understand the basic ideas behind machine learning and neural networks. Using these ideas, we will start creating a generative adversarial network, or GAN. And from there, we will combine this understanding of classical GANs with quantum computing to understand the quantum GAN. First, let us understand artificial intelligence and machine learning. Artificial intelligence covers the broad range of topics that try to mimic how our brain functions and processes sensory data. To understand artificial intelligence and machine learning, we should first understand how our brains work. So our brains use a set of neurons or neural networks to take input data, process it, and tell what to do with the processed data. We can replicate this behavior on a computer by creating what we call an artificial neural network, or ANN. These ANNs have several input layer. They have an input layer of neurons, several hidden layers, and an output layer. An example ANN is shown on the right side of the screen here. Each of these neurons in the layers are connected to the next layer by an edge with a certain weight. Any neuron in some certain layer takes the weighted sum of all the previously connected neurons. And when we train these neural networks, we keep updating these edge weights to get more accurate results. And yeah, so this would be an example of, again, this would be an example of a neural network with one hidden layer, but you can have several different hidden layers. And artificial intelligence systems use these neural networks for several different applications. Machine learning models are specifically systems that train on extracted features from data. For example, let's say we were trying to recognize the shape of different objects given several images. An example of extracted features could be for like the shape of an apple. And oftentimes you'll also hear what deep learning is. Deep learning is specifically a subset of machine learning where we use the original data instead of the extracted features to find patterns. So for example, rather than looking at the extracted features from that image of the apple, I would just be given the image of the apple, and the deep learning model would try to figure out the shape from there. One more key concept in neural networks is the distinction between supervised and unsupervised neural networks. So when we say supervised learning, that's when an expert is there to supervise how the output data should be. For example, let's say we're trying to train a neural network to classify different images as dogs or cats. An expert should be someone who can specifically say this image is a dog and this image is a cat. The neural network will basically train to match the get the outputs that match what the expert has classified as dogs and cats. But one main drawback of supervised learning is that it takes a long time to sometimes label all the input data. On the other hand, we have unsupervised learning. And as the name suggests, there's no expert to label the data for us. So if we are using our like dog and cat classification example, this is when nobody is there to say this image is a dog and this image is a cat. One main method to get around this is by clustering different samples that are more related to each other. For example, the model could look at certain dog and cat features and put the images with certain, like the dog features in one group and the cat features in another group. The main drawback of unsupervised learning is that since there's nobody to validate how our model trains, the model might give inaccurate results. So this brings us to generative adversarial networks, or GANs. GANs are unsupervised models that have two key features, a generator and a discriminator. So the generator will try to create samples to trick the generator, and the role of the discriminator is to compare these samples with the real data to see if these generated samples are real or fake. So we say that this GAN has reached a Nash equilibrium when the discriminator assigns a 50% probability of samples being real or fake. So in this manner, the usefulness of GANs is twofold. First of all, the model can learn the distribution of the real data, but can also produce very realistic samples. And we can see this usefulness in several different applications, primarily in image-based operations. The example on the slide is a GAN model with changing the image of horses into zebras and vice versa. GANs have also been used in cryptography, anomaly detection, conversions between images, text, and speech, and several other applications. So with this information on GANs, we have one more concept to understand before coming to quantum GANs, and that's the distinction between what is classical and what is quantum computing. So classical computing is really the computing that we see every day in devices all around us. Data stored as binary information or a stream of ones and zeros called bits. And we can define this classical computing to be the operations and processing done on these bits. In an electrical circuit, this is achieved using transistors where 0 is an off state and 1 is an on state. On the other hand, quantum computing is operations and processing done on quantum data called qubits. So while classical bits can only represent discrete 0 and 1 states, qubits can represent any linear combination or what we call a superposition of these 0 and 1 states. The quantum equivalent of transistors is what we call quantum gates. Mathematically, these quantum gates are represented as rotation and reflection matrices. So one main property of qubits, aside from superposition, is the property of quantum entanglement. If two qubits are entangled, their states remain linked or perfectly correlated, no matter how far apart they are. For this reason, actually, Einstein called entanglement spooky action at a distance, since qubits can remain entangled even at opposite corners of the universe. The main advantage of having entanglement is that the number of operations on a quantum computer will exponentially grow with the number of qubits. Another advantage, even more pertinent to this project, is that with entanglement, quantum models can learn correlated distributions faster than classical models. So using these quantum ideas, we can now represent a quantum GAN. So the quantum GAN, the structure is almost the same as the classical GAN. You still have the same connections between the generator and the discriminator, except now we are using quantum data. So the output will be represented as a real or fake state. The generator and discriminator still maintain their functions of learning the probability distribution of the input data set, but now they're in a form of a quantum circuit. This means that the generator and discriminator circuits will compete, and the generator tries to fool the discriminator into thinking that a sample it created was real. So this causes the GAN to, of course, produce more realistic samples. And training on a classical GAN, as we saw, we tried to adjust weights to update the model. But here, since the generator and discriminator are quantum circuits and they're parameterized, meaning that there's a real number attached to each one of the probability of the states. So how to train the quantum GAN? Well, we can adjust these parameters to get better and better outputs. So a few main advantages of using this quantum GAN over the classical GAN is that classical GANs take a longer time to reach the Nash equilibrium than the quantum GAN. So again, just to remind you what Nash equilibrium is, it is the state where the discriminator cannot distinguish between whether a generated sample is real or fake. So this means that quantum GANs can actually solve optimization and sampling problems that are much harder for classical computers and learn correlated probability distributions when there are multiple entangled qubits, and do this at a rate much faster than classical computers could do. Now, of course, these quantum GANs do come with a slight challenge, and that's mainly transforming the input data into equivalent quantum data. So the idea to overcome this challenge is to synthesize several quantum gates to create an input vector. So what do I mean by this? Well, there are four key universal quantum gates: the control knot, C naught, or Hadamard, the H, and the rotation in the Y and rotation in the Z. We call these RY and RZ gates. So their respective rotation and reflection matrices are shown on the right of the slide here. And by combining several of these gates, we are able to get a desired feature input. So using this feature input, we can create a more sophisticated and robust quantum GAN. So to summarize, we've essentially understood how quantum generative adversarial networks, they're essentially machine learning models that are both powerful and practical. But moving these into a quantum setting to create quantum GANs is promising because they are able to converge faster and have an easier time learning features of real data. Thank you so much for your time.
Ram, thank you very much for that incredibly exciting presentation. As a quantum physicist myself, I appreciate the excitement that combining quantum mechanics with machine learning brings. So if you have questions, audience members, please note them either in the Q&A channel or pull them for after the talks. Next up is Varun Venkatesh, and please join us on the stage.
Sure. Just give me a second.
Actually.
Okay, yeah. Can you guys see my screen? Hello?
Yep.
Can you guys see my screen?
Yes.
Okay. So should I start?
Please start, yes.
Okay. So hello, my name is Varun Venkatesh. I'm from Dublin, California. And my presentation is about my project, a statistical model for identifying missing and unclear signs of the Indus Valley script. My mentor was Dr. Ali Farghali. He formerly worked at Stanford and the University of Michigan, and he used to be a professor of linguistics, who also acquired a PhD at UT Austin. So to begin my project, let me tell you guys a little bit about the Indus Valley civilization. So the Indus Valley civilization thrived from about 3300 to 1800 BCE, and it was located in the northwest part of the Indian subcontinent. It extended to a region of about 800,000 square kilometers, and the Indus people are very well known due to their drainage and water supply systems. So as shown by these two images here, these are archaeological excavation sites, and so far, only 10% of these sites have been excavated. Right now, I'm trying to analyze something called the Indus Valley script, and so far, it is considered logosyllabic and it's completely undeciphered. These two images show the Indus script written on seals, tablets, and pots. Right now in my project, my goal is to extend the current work of people at University of Washington and Harvard, and I'm using advanced language models and algorithms on the newest corpus in order to extend that work. So let me first introduce you to something called unclear symbols. In the Indus Valley script, there's something known as unclear symbols, and basically they are symbols in a text that have been lost due to time and broken off. As you can see by these two images, these are two prime examples of unclear symbols. And so far, in something called the text corpus, and the corpus basically means all of the text in the Indus script, right? About 10% of these texts are, missing and unclear, right? My goal for this project is to identify missing and unclear signs using statistical methods. So right now I'm using something called the ICID text corpus. It is the most recent corpus, and it represents each sign as a 3-digit number. There are about 700 unique signs in the ICID text corpus, and as shown by this image here, this is how the ICIT text corpus represents the Indus Valley symbols. So initially, I did start with about 4,500 texts, and I had to do some data cleaning. So what I did was, for my data cleaning, I removed any text that had an unknown direction, right? If it was multi-line, had an unknown direction, or was multi-part. After all of this, I was left with about 2,223 texts, and about 100 of these texts were single missing signs. So the reason I did this was so that I could perform various statistical analysis on them. So the statistical analysis of the text that I've done has produced this graph, which shows the length distribution of the text. And it basically shows the signs of a text plotted against the frequency. As you can see by this graph, there aren't a lot of long texts in the corpus. So right now, there's an average text length of about, between 4 to 5 signs, and about 95% of these signs are written from right to left. So as shown by this next image, the Indus Valley script actually follows the Zip-Mandelbrot language distribution, which is just a benchmark language distribution. So as you can see by the graph, a small number of signs were found with high frequencies, and the long tail of the graph is made up of signs with lesser frequencies. After that, I moved on to something called n-grams, and n-grams are n signs appearing together. So these three charts show something called bigrams. As you can see, there's one sign here. Unigrams, there's one sign here. Bigrams, there's 2 signs, and trigrams, there's 3 signs, just like the name suggests. So what I did was I used sign frequencies and sign probabilities, and I computed them for unigrams, bigrams, and trigrams, and I created these 3 charts, which show the most frequent sign for each n-gram, right? So this was very useful so that we could build a language model. So what language model am I talking about? I'm talking about the Markov chain language model. The Markov chain language model is a language model that uses a conditional probability of the sets of signs before it in order to find the unclear sign at the end or of the text. So here's a visual representation of it. So our goal here is to find signs that have a non-zero conditional probability of forming a trigram with these 2 symbols, right? And over here, right, the candidates are the jar symbol and the water carrier symbol, right, as shown by this image here. Right now, I took my data set and I split it between 80% training and 20% test, right? I built various language models by feeding the full corpus text, right, generating n-grams and conditional probability for each sign forming different n-grams. So far, I've used Jupyter Notebook, Python, and LTK. And within my test set, I have used these softwares to remove a known sign and change it to an unclear sign on the test set, as shown by the image here. So after all of this, I have devised my 2 most useful algorithms, sign fill and start and sign fill and full. I will introduce them right now. The sign fill and full algorithm is an algorithm that starts with around 5 symbols and goes all the way down to the bigram for each missing sign. So from the corpus, what it does is it finds signs that fit the missing sign, forming an n-gram with a non-zero score. So look at this on my slide. It keeps trying to match, and if you didn't get a match until the end, you would just use a positional probability. So right now, after I've done all of that, I made 100 runs with signs, and I made them unclear at random locations in the text. I used my sign fill and start and sign fill and full algorithms on top of my current language models. And what I did was I measured how many times that I found the correct sign. So this allowed me to use the best model to find the real unclear signs. And I ended up with figuring out that the sign fill and full algorithm on top of the Lidstone language model achieved me a 63% identification rate. And this identification rate is amazing. It will immensely help researchers to identify the missing signs in the future. And here's a chart just for comparison, right? So if I just went and randomly replaced the symbols, I would have a 1.4% identification rate. However, if I did positional probability, like so many others have done in their papers, I would have about, a 7% identification rate. I achieved a 63% identification rate. Here are my results. Here's a chart with 10 unclear texts, the 5 most probable signs that could replace them, and this column shows the first most probable sign that could replace it, right? So in conclusion, I found many things about the Indus script. First, the Indus script has patterns that encode that of a language, right? It also has groups of 3 and 4 signs, right? And these groups of 3 or 4 signs may represent a concept. And I know this because my sign fill in full algorithm has a 63% hit at 10 identification rate. This identification rate will immensely help to enrich the corpus and help in the overall deciphering effort. I have shared all my results and all my code with the Indus script research community. And if you have any questions, or if you just want to take a look at my code, go to my Git repo. If you want to look at any of my past projects, go to my dev post. And if you have any questions, just go ahead. Thank you.
Varun, thank you so much for that excellent presentation. Very exciting work. And it's fantastic that you've already shared this with the broader community. So to the audience members, please note down your questions. There will be opportunities to ask them at the end of all presentations. So thank you, Varun. With that, I will invite Anay Poghosyan to present next.
Hello, my name is Anay Poghosyan, and I'm from Los Angeles, California, and my project is on applying random forests to the classification of forensic evidence. So, blood spatter analysis is a crucial part of the criminal investigation process. Blood spatters reveal the position of the attacker, position of the victim, and what I'm focusing on today, which is the weapon used in the crime. The goal of my project is to use machine learning to classify bloodstains as either gunshot or blunt force induced. The benefits of this project are to increase the efficiency and speed of preliminary investigation in the criminal investigation process and to bring closure to the families of victims. So there are 3 main types of blood spatters, and today I'm focusing on a specific type of blood spatter called the impact stain, which is created by an object hitting the victim at a very high velocity. There are 2 main types of impact stains. They can be either gunshot or blunt force induced. An example of a gunshot stain is this blood stain right here, and you can tell that it's a gunshot stain because the droplets are very small, uniform, and circular in shape. In contrast to this, a blunt force stain the droplets have much larger area, they're more elliptical and irregular in shape. They also have these kind of tails, as you can see in the photo. So the research paper that inspired this project was the automatic classification of bloodstain patterns caused by gunshot and blunt impact at various distances by Daniel Adinger. So I got the data for my project from a publicly available dataset of 64 laboratory-created blood spatter images, and this dataset was created by the same team that wrote the research paper that inspired this project. The dataset is available on the National Institute of Justice website. So at this point in time in my project, I had 64 blood spatter images and I didn't have any usable data. So what I had to do was use feature extraction to get the actual data from the images. I created a 4-step process that is performed entirely in Adobe Photoshop in order to extract the features. The first step in this process is to overlay a 1 centimeter by 1 centimeter grid onto the image. Next, an optimal region on the grid was selected and only that area was analyzed, and I was looking at the exact same square, the exact same region on every single image in order to keep the data consistent. Next, I use Photoshop's Magic Wand tool, which selects pixels of the same color in order to select all of the red pixels. And then by creating a selection, I was able to use the built-in record measurements function to log the measurements of every individual droplet. However, this gave me a lot of data for just one image, so I had to consolidate it all into a single row on a CSV file. So what I did was I had this giant data set for every single image, and I would just average out all of the values, and that would constitute one row in my CSV file. So in the world of machine learning, 64 blood spatter images is not a lot of data to work with. Instead, I had to use a process called data augmentation to artificially multiply the amount of data available in order to increase the accuracy of my algorithm. So in order to create more data, the process of feature extraction was repeated with multiple chosen regions on an image. So just to show how this works, I had selected an optimal region on each of my blood spatters to analyze, and for data augmentation, I just went ahead and selected a different optimal region, and I would look at that same area on every single image. So in order to code my random forest, I built my random forest off of a publicly available random forest in the UCI machine learning repository that classified sonar images. And just to clarify what a random forest is, it's a Python algorithm that is used to classify data. It's made up of multiple decision trees, as I've shown right here. One decision tree uses conditions to classify data, and multiple decision trees that run at the same time constitute a random forest. So at this point in time, my random forest was up and running, but the accuracy was not looking pretty. To increase the accuracy, I used a process called tuning, where you change these hyperparameters or aspects of the random forest, such as the size, the depth, and the number of trees, in order to increase the accuracy. I would change the hyperparameters little by little to see how they affected the accuracy and try to maximize the accuracy as much as possible. I used matplotlib to graph the different accuracies at different settings of the hyperparameters. And as you can see in this graph, when the maximum depth of my random forest was brought to 8, the accuracy plummeted, but when the maximum depth was at 7, the accuracy spiked. So that basically showed me that I needed to set my max depth to 7. Additionally, I plotted the number of trees versus the accuracy, and the same pattern is shown here. At 100 trees, my accuracy plummeted, but my accuracy spiked at 10 trees. I was able to achieve an accuracy of 93% on my random forest. So the impact of this project is to increase efficiency and speed in the criminal investigation process, and this eventually helps families of victims to have closure. Because the STEM field is always growing and changing, my project is also on the forefront of combining machine learning and forensic sciences. However, there's always room to improve, and I think accessibility to more data would have significantly increased the accuracy of my algorithm. Unfortunately, finding data for forensic sciences-based projects is extremely difficult, as a lot of it is classified and not readily available to the public. Thank you for listening to my presentation, and I am more than happy to answer any questions that anyone may have.
Thank you so much, Anna, for this great presentation and sharing these exciting results. I already saw there were a bunch of questions that we'll get to after the final presentation, which will be given by Anay Joshi. Anay, please join the stage.
So hi all, my name is Anay Joshi, and today I'll be talking about my research on the correlation of various economic and social variables on carbon emissions. And I was mentored by Clayton Greenberg. Sorry. I'm going to start off my presentation by giving a brief overview of the previous literature and work that I used to help me with my research. So the first piece of literature that I'll be reviewing is called The Impact of Environmental Policy Stringency on Air Quality by K. Wang and Ming-Yi Yan, Yiwei Wang, and Changping Chang. So what they did was very similar to what I did for my first research question, which I will go more in depth later on in the presentation. The main difference between my research and their research is that my visualizations were different And I also investigated a couple of different variables that they set as their control variables. The data sets I used were sourced from the OECD, where I got my environmental policy stringency data. And I'll be abbreviating this as EPS for the rest of the presentation. My next data set that I sourced data from was from Our World in Data, and I got carbon dioxide emissions per capita data from this data set. The next data set that I sourced data from was from the World Bank, and I got total population data from this data set. And the last data set that I sourced data from, which was for GDP data, was from CAG. So my first research question is, does the degree to which climate change laws are enforced correlate to the ideal trend? So before I dive into this research question, I just want to mention that the metric I use to classify the degree to which a climate change law is enforced is called EPS, or Environmental Policy Stringency. It is a value between 0 and 4, where the larger the value is, the stricter the environmental policies were for that country at that point in time. So our first visualization is a box plot, which we can see right here. We rounded all of the environmental policy stringency values to the nearest integer to get a nicer box plot. And we can see there's an ideal trend happening over here, where the larger the environmental policy stringency is, or the stricter the environmental policy is for a country, the less carbon dioxide is being emitted per person. But we can see for the EPS value of 0, this completely offsets the data, as the median for the EPS value of 0 is less than the 25th percentile for the EPS value of 1. And the 75th percentile for the EPS value of 0 is less than the 50th percentile for the EPS value of 1. To better understand the box plot above, we can split each of the box plots into histograms. And this better shows us the distribution of data, where the x-axis represents the carbon dioxide emissions per capita. We can see sorry, my Zoom thing is interfering. For EPS value of 0, most of the data is centered from 0.0 to 2.5 emissions per capita. For the EPS value of 1, we can see a lot of the data centered around 10.0, which is kind of consistent with the box plots that we saw above, where the EPS value of 0 performed a lot better than the EPS value of 1. We can see for the EPS value of 2, the data is shifted to the left, which was consistent with the box plot, as they did have less carbon dioxide emissions per capita for the EPS value of 2. For the EPS value of 3, it is also shifted a little bit to the left, which is also consistent with the box plot. And for the EPS value of 4, the data is also shifted a little bit more to the left than the EPS value of 3, which is consistent with the box plot. So another way to visualize this data is through a scatter plot, and each point is for a different country's EPS value at a specific point in time. And in this case, it is not rounded, as we can see, as there are dots between the integer values of 2 and 3, and so which represents like decimals. So we can see this ideal trend in the main swarm, where as the EPS value increases, the carbon dioxide emissions per capita decreases over time. We can see that there are clusters near the EPS values of 0 and EPS values of 1, which are the reasons why the box plot and the histogram for EPS value of 0 and EPS value of 1 offset the ideal trend. In this scatter plot, we also added a new dimension, which indicates the year at which the data was taken, and this is represented by the color of the dot. And we can see as the dots get lighter, which indicates more recent years, the EPS value is increasing as well. As we can see, most of the dark dots are towards the beginning or towards a lower EPS value, and most of the light dots are towards the end, which is towards a higher EPS value. So my second research question is, in what way does GDP correlate towards the carbon dioxide emissions per capita over time? So the way that I kind of visualized this data is by graphing the correlation coefficient between GDP and carbon dioxide emissions, and with the versus the x-axis of time from years from 1960 to 2020. So the way correlation coefficient works is that any values close to -1 indicate a very strong inverse relationship between the two variables. Any values close to 0 indicates almost no relation between the variables, and a value close to 1 indicates a very strong positive relationship between the variables. So you can see at around 1960, we start off with a very high correlation coefficient value, which means that carbon dioxide emissions was very strongly associated with GDP or the economy. But as time progresses, we can see that this correlation coefficient is decreasing over time. This indicates that slowly carbon dioxide emissions are growing less and less associated with economy, which means that as economy may improve, that doesn't necessarily correlate to carbon dioxide emissions increasing over time. This is very important as it shows that our economy is depending less and less on systems that require carbon dioxide emissions. My last research question is, how does the total population correlate to the carbon dioxide emissions per capita? So to visualize this data, I put two line graphs in a span of one where there are two y-axes, one for total emissions and one for population. So total population is represented by the red line and the total emissions is represented by the blue line. We can see that initially both of the trends were very similar. And sorry, it's important to note that even though it says 0 to 25, this is years since 1990. So 0 represents 1990 and 25 represents 2015. So we can see initially the trends of both of these variables were very similar. But at around 2005, the total emissions trend reversed, where it started decreasing even though the total population trend continued to stay the same. This indicates that after a while, total emissions grew less correlated with total population. It's important to note that both of these variables had a significant drop at around 2013, which is because many countries stopped reporting their data at that time. But it's important to note that even after this drop, the same trends were visible, where total emissions trend was decreasing and the total population trend was increasing. So in conclusion, does the degree to which climate change laws are enforced correlate to the ideal trend? We saw that for EPS values of 1 to 4, there was a slight decrease in carbon dioxide emissions per capita. But for the EPS value of 0, it completely offset that data, which is why we cannot say that the environmental policy stringency results follow the ideal trend. For the second research question, in what way does GDP correlate towards the carbon dioxide emissions per capita over time? We saw with the correlation coefficient versus time that it was slowly decreasing over time, which means that they grew less and less associated with each other. So GDP relation between GDP and carbon dioxide emissions per capita is decreasing. And lastly, how does total population correlate to the carbon dioxide emissions per capita? We saw originally that at around 1990, they were having the similar trend. But after a while, the total carbon dioxide emissions dropped off while total population continued to stay the same, which means that even though initially they were very correlated, they stopped growing correlated over time. Thank you for listening, and I'm happy to answer any questions.
Anay, thank you so much for that exciting and excellent presentation. So I now ask the audience members to join me in applauding all our speakers today. Obviously, today we celebrate the incredible work and achievements of all of the speakers, Anay, Anna, Varun, and Ram. And now we still have a little over 10 minutes left to ask all the questions that you've been holding off on asking up until the end. So again, thank you to all our speakers. And let's jump into the questions. So I'll actually start with a question myself. And the first question is to Ram. So Ram, you talked about adversarial networks and quantum computing. And can you speak a little more to the value of combining these, and what would we be able to do that we wouldn't be able to do if we just only had classical computers?
Sure, yeah. So again, as I mentioned earlier, I think I talked about how the quantum GAN does converge faster towards this Nash equilibrium than the classical GAN. The main advantage where we can actually apply this is, well, so first of all, in when we are creating different samples, we see less and less improvement over time in the classical GAN when you're training for a longer time. And this is what we are trying to improve by going to a classical GAN. So especially in, for example, cryptographic models, you want to be able to take in large amounts of numerical data and you want to be able to, for example, let's say you're creating like a cryptographic key or some equivalent, training the GAN for a long amount, it takes a long time to actually get like, for example, a good cryptographic key. But when we are using this quantum GAN, we are able to improve the speed at which we are able to process this data. That's one of the main advantages as well. And as a result of improving the speed, we are in the same amount of time as the classical GAN would have taken, we are able to get more realistic samples.
Got it. Thank you, Ram. There is actually a question from the audience. Lucy, Lucy, can you actually come and ask this question live? I don't know if that's possible here. Allowed to talk, yeah.
Hi, can you hear me?
Yes.
Okay, great. Yeah, so sorry, Ram, I missed your presentation, but I was wondering for Varun, where did you first learn about or like become interested in the Indus Valley civilization? I've never heard of that.
Yeah, that's a great question. So a year ago, I was actually reading a couple of books on it, and I was sort of inspired by my father as well. So my father has he has a pretty good understanding of it, and he's kind of a history geek. So he knows a lot about, Middle Eastern civilizations, Indian civilizations, just things like that. So I got, yeah.
That's exciting. And what was the most surprising thing you learned, Varun?
The most surprising thing I learned, so it was probably that the unclear symbols could actually be used to not only figure out the entire language as a whole, it could also figure out, his mysteries of the past and so many other things that we don't know about the Indus Valley civilization.
Wow. Yeah, all these projects just blow me away. And using these sophisticated statistical methods to study something as old as the Indus Valley just really shows me how this interdisciplinary approach can unearth new knowledge that even the best scholars without technology might not have been able to get their hands on, which for me is super exciting. So there was actually another question for Anay, which is, do you prefer different visualizations like box plot versus scatter plot? How do you select which data visualization to use?
Yeah, so throughout my research, I actually had a lot of different visualizations. Some of them proved to be fruitful. Some of them gave me no information at all. So the visualizations that I showed in my presentation, all gave me various forms of information. So in the case of the box plot, we were better able to see how the different carbon dioxide emissions were performing for the different EPS values. And for the histogram, we could better see the distribution in a horizontal perspective, where we could see a lot of the data shifted to the left. For the scatter plot, we were even able to add that extra dimension for time. So that was quite nice. For the correlation coefficient one, I wanted to see its trend over time. So I did throw many different visualizations at it, but I think the line plot kind of showed the best, gave me the most information. And for the last one, for the 2 line graphs, like I said, I threw a lot of different visualizations at it. And in that case, that gave me the most information. So I don't necessarily prefer a certain visualization, but there were some that did give me a lot more information than others.
Got it. Great. Thank you so much.
Really quickly, I just wanted to expand on the question that Lucy asked me before. So yeah, so she asked me, how did I get interested? How did I first learn about? And I kind of addressed that. But I wanted to also address how how many other people have done this work, but they've done it on different corpuses. So in my presentation, I did explain that I did my work on something called the ICID corpus. And as far as we know, no one else has done my similar work on this corpus. So far, someone has done work on a more old corpus. University of Washington and a team in India have worked on the corpus known as M77, and they use a bigram model. However, you can't really, compare their project with mine's because they use different corpus and they also use different measures. So the main thing that got me interested and that got me, that helped me figure out what methods I was going to use was the work done on Babylonian cuneiform. So they actually did a very similar work to mine. It was in order to identify the missing signs, and they used a similar measure to evaluate the model, just like I did in my work.
Got it. Thank you, Varun, for sharing that. It's super exciting and very interesting project. Anna, there's a question for you from Lucy. Let me just allow Lucy to ask that question live.
Hey, Anna, I'm curious, like, where did you source the blood spatter sample photos from? Like you mentioned you had 64. Did they all come from the same place? How did you choose them?
Yeah, so they all came from a publicly available data set. They were all from the same data set, and it's available on the Department of Justice website. And it was also used in a different research paper, and they were all made in a laboratory. But yeah, it all came from the same data set. Unfortunately, I couldn't get my hands on any more data just because it's difficult to find for forensic sciences. So that's when I turned to data augmentation, just to kind of multiply that data and make it usable for my project.
Very cool. And if I can ask a quick follow-up, do you have like a favorite crime show or crime podcast that that you enjoy?
I don't necessarily have a favorite, but I love to listen to true crime. It's just really interesting, and I'm so thankful that I got the opportunity to make a project in the same like field and just tying together machine learning and forensics.
It's so exciting, being able to bring together these different fields. Anna, do you think that if you had more data, any of your conclusions might have changed?
I definitely think my accuracy would have gone up by a lot because data augmentation for me was just more of a last resort, and I really wish I did get my hands on more data. So I do think it would affect the accuracy drastically.
Got it. Thank you. So I actually have a question for Ram. Ram, you mentioned that the entanglement can grow exponentially in a quantum computer. Do you also know some drawbacks of increasing the system size and some of the limitations of making entanglement scale up?
Yes, that's actually a very good question. And this actually addresses a more general idea in quantum computing, which we call it like almost an error correction. So when you increase the size of any quantum circuit, one of the main drawbacks that you will start noticing is that there will be some interference between different qubits within the system, some unwanted environmental interference that can actually cause more random error within the circuit. Most of what I've described here actually can account for that error through just the way that the GAN trains. But it is not, this is not by any means like a perfect, like get rid of all the error. So to address your question, yes, increasing the size does have one drawback, and that is mainly the increased unwanted error within inherent randomness within these quantum circuits.
Got it. Yeah, that's very interesting. And as a quantum physicist myself, I keep thinking about some of these limitations, but of course, there are so many exciting things. Anay, I have a question for you as well. So obviously, carbon emissions are something we all think about nowadays as we read the news and we see world leaders get together. If you had one recommendations for decision makers based on your work and research, what would that be?
My one recommendation was, because as we saw with the environmental policy stringency, strictening the environmental policy may have a slight improvement for carbon dioxide emissions per capita. We saw with the EPS value of 0 that it was not always the case. So I'd say enforce your environmental policies, not necessarily to be more strict, but focus more on different methods that'll make it more effective, because strictness, as we saw, was not necessarily the most reliable way of decreasing carbon emissions.
Got it. And what kind of future work do you think would be able to give even more insight into the right course of action?
So maybe comparing carbon emissions to other variables that are a little bit more specific to the world. So I investigated GDP and environmental policy and total population, which are very broad variables. But if I were to focus on more specific variables, we can look at different correlations that can potentially lead to a causation with further scientific analysis. And then that causation can help different policymakers make better environmental policy decisions.
Got it. Any other questions from the audience or from any of the panelists to the other panelists? I have an infinite number of questions, but I want others to ask too. Well, Anna, do you know if any of these techniques are actually being used in courtrooms or in police departments?
Because this is a pretty new field combining forensics and machine learning, I'm actually not sure, and a lot of it isn't really talked about because a lot of like criminal investigations aren't really like broadcast to the public. However, I do think it would be really important to integrate machine learning into the criminal investigation process because it could really help with efficiency and just to bring closure to the families of.
Got it. And is the issue right now that things are just too slow or inaccurate?
I think both of them are an issue, but my biggest problem is that it's very slow because when you have to analyze tens of thousands of bloodstain images, it's so much easier to just automate the process.
Got it. Got it. That makes sense. Any other questions from the audience?
Oh, actually, I had another quick question for Anna. What was the why did you choose to use specifically the random forest model? Of course, there are several other machine learning models for images, but why specifically the random forest?
That's a great question. So I thought it would be the best fit for what I was trying to do. I was really getting two different outputs. It was either gunshot or blunt force induced, and I thought since there's only like it's just a binary like kind of thing, then the random forest would be the best fit for.
Got it. Now, some very technical questions, which make sense as every panelist here has excelled in computer science and using these techniques to analyze their data. Any other questions? Question for you, Varun. So the Indus Valley civilization was obviously a pretty extended civilization, as you showed. Do you know if some of the scripts that you analyzed did show up actually in other parts of the world as well, or even the Indian Peninsula?
Yeah. So right now, what I do know is that there are many other river valley civilizations that thrive, right? Just some examples, the Egyptian Nile civilization, in China, the Yangtze, Mesopotamia, and, Euphrates and Tigris civilizations. As far as I know other sites, such as, Mohenjo-daro, Harappa, and Dolvira, but most of these, scripts only come from these sites. So if you were to, generalize it across multiple sites, I'd say Mohenjo-daro and Harappa are the two main places you will find these scripts. Yeah, that's about it.
Got it. Incredible to think about how these people wrote these scripts that probably they never expected to be analyzed by the sort of techniques we have today. And it makes me wonder what lies beyond. Do you have thoughts what kind of techniques we might be able to use a decade from now?
Absolutely, yeah. So I do know for a fact that there is no relation to any other script across the world, right? It doesn't relate to any other script. But I do think that my identification of 63%, right, it will immensely help researchers, right? As you know, I've already shared everything. I've shared all my code. I hope that it can be used to fully decipher the language, because currently the Indus Valley script is undeciphered. It is a major mystery, and there's a huge research community going after it, finding various methods and trying to, decipher it. I think my work will definitely help the cause.
Got it. That's great to hear. All right, we actually ran over by 3 minutes. So I just wanted to again thank all our wonderful presenters who not only did many, many months of great work, but also prepared these awesome presentations for us and for posterity, as obviously we recorded this and we'll be make it shareable by others. I'll also note that we had team members in the audience who are scoring these talks. So obviously, all of these presenters will be competing for the prizes that we have up for grabs. And I just wanted us to again applaud the presenters and celebrate their many months of work and great contributions to science and scholarship. And thank you very much. Now we conclude this section. And in just 1 minute, we have Professor Michael Puett's presentation starting at 9:15 my time, 12:15 Eastern time. So please join us for the keynote address. It's going to be really exciting. So thank you, Anay. Thank you, Ram. Thank you, Anna. And thank you, Varun. See you later. Bye.